So, welcome again to the new lecture of properties of materials. So, this is going to be the last lecture of this course. So, in which we are going to mainly finish off the semiconductors with the extrinsic semiconductors and then summarize the course. So, essentially in the last lecture what we discussed was, in the last lecture we talked about semiconductors as materials with band gap smaller than, let us say, 2.5 to 3 eV. Okay. Silicon is the most common semiconductor, it has a band gap of 1.1 eV, and the electron concentration in semiconductors is proportional to exponential of minus Eg by 2 kT. Since as we saw that voltage required to move an electron from conduction to valence to conduction band is very large, thermal excitation is a very useful means to create some carrier density, and this is, so this N is equal to capital small n, which is nothing but Nc into Nv to the power half into exponential of minus Eg by 2 kT. So, in this expression you can see as Eg increases, N decreases, and as T increases, N increases. So, this N is basically, if you look at this picture, this is Ec, this is Ev, this is Eg. So, this is conduction band and this is valence band. So, Ev is the conduction and valence band edge and Ec is the conduction band edge, and you can measure the energy either from the bottom or from the top, from the vacuum level, depending upon how you may want to work. And the Fermi level for an intrinsic semiconductor lies at Eg by 2 value, or you can say Ec minus Ef, Ec minus Ef, or Ev minus Ef, okay, or you can say Ec minus Ev divided by 2, that is also possible. Okay. So, now so basically we saw that probability of occupation is basically we sort of reduced it to 1 over exponential of Eg by 2 kT for a semiconductor, considering Eg was equal to Ec minus Ef, alright. And number of electrons is basically determined as, you can say, Pe, probability of occupation, into density of states, and you have to integrate it for all the energies from Eg to infinity, sorry, Ec to infinity, where Ge is nothing but the density of states. We have not talked about it, but basically density of states mean number of states per unit volume, per dE, per a small energy state dE. Okay. So, basically if you plot this, so let us say this is the conduction band, this is the valence band. Okay. So, this is Vb, this is Cb, okay, and this is what we have Eg, this is where we have Ec, this is where we have Ev, and this is where we have Ef, and this is the scale E. So, now if I want to plot on the same plot, let us say E versus Pe or Fe, I can't remember what I wrote in the previous lecture, but so we know that at 0 Kelvin Pe goes like this at 0 Kelvin. At some finite temperature it will now become, so around 0.5 it will sort of so this will be the sort of relation at T greater than 0 K, and as you increase the temperature this curve will, sorry. So, as you keep moving the temperature, if you plot now the electron concentration at the same column, so this is N and this is E, and N is nothing but product of, let us say, Pe into density of states, the states available. We can see that in this region there are no states available. So, no states available. So, if dE is 0 in this region, then N is also going to be equal to 0. So, as a result, what happens is that when you plot N in this semiconductor, so you will create, most of the N is going to be around this. Correspondingly, you will have another region which is holes. This is N and equal number of holes. So, for an intrinsic semiconductor, we write N is equal to Nc into exponential of minus Eg by 2 kT, Nc Nv to the power half to Eg by 2 kT, and this N is called as Ni. So, this is intrinsic carrier concentration, and this means Ni is equal to N, which is equal to H. So, this is number of electrons in conduction band, and this will be number of holes in conduction valence band per unit volume. So, this is also per unit volume. So, Ni is equal to N is equal to H is equal to Nc Nv to the power half exponential of minus Eg by 2 kT for a intrinsic semiconductor. Intrinsic means pure semiconductor, which does not have a lot of impurities in it, and we will see, you can find out easily that the electron concentration basically is not very large. Electron concentration happens to be, N happens to be essentially nearly around 10 to the power 16 per meter cube at room temperature in these materials, in silicon, let us say, in silicon. This is a very small number. So, this is a very small number, because if you calculate now the conductivity of silicon with this. So, now conductivity, if you want to calculate conductivity sigma now will be equal to, for a metal it was N E mu, okay. For a semiconductor it is, now you have two carriers N E mu plus N P or NH E mu. So, this is electron concentration and this is hole concentration, okay. So, they have similar charge. So, for an intrinsic semiconductor, Ne is equal to Nh. So, sigma can be equal to Ne into E is also common. This is mu E, mu H, but electron and holes have different mobilities because they have different effective masses. So, if you take the values of mobility, the value of mobility for electron, so in silicon, mu E is equal to 0.14 meter square per volt second, and mu H is equal to 0.05 meter square per volt second. And if you plug in the values and if you take E as 1.6 into 10 minus 19 coulomb, you will get a sigma value of 1 over 300 ohm meter inverse. So, essentially you are saying it's basically nearly 3.3 into 10 to the power minus 3 ohm meter inverse. This is very low conductivity as compared to metals, and this is not good enough to make silicon very useful. So, as a result, what you do is that, so this is about pure silicon. So, to make silicon useful, or to make any semiconductor useful, we dope it with intentional or targeted impurities. So, doping means basically substituting silicon with another atom of different valence. So, silicon, if you look at the group 3, 4, 5. So, this is group 3, this is group 4, this is group 5. So, if I look at the periodic table, in group 3 I have, in group 4 I have silicon, okay. Let's take silicon here. Group 3 has boron, aluminum, let's say, I will not go down, and group 5 has top of the ones, we have nitrogen and phosphorus. It turns out, so if you now replace, if you put some of the nitrogen or phosphorus in silicon, typically phosphorus and in this case boron. So, if you put phosphorus in silicon, then let us say this is the configuration we have, okay. So, this is silicon, this is pure silicon, okay. Let us say silicon is surrounded by 4 neighbors, this is pure silicon. Now, let us say if I replace one of these silicon with phosphorus, so now this is not silicon, this becomes phosphorus. Now, phosphorus has an extra electron because phosphorus is plus 5 and silicon is 4 plus. So, as a result, what happens is that in the energy gap, so this is valence band, this is conduction band, you had some electrons here, some electrons here because of thermal excitation, and you have some holes here correspondingly, okay. This is for pure silicon. So, for pure silicon, Ne was equal to Nh, which will be about 10^16 per meter cube at room temperature. When you put in phosphorus atoms in there, let us say I put in phosphorus atoms of the order of 10^18 per meter cube. So, let us say phosphorus is we call it as a donor atom. So, let us say Nd is donor concentration, okay, and this happens to be phosphorus. So, when I put phosphorus in it, what phosphorus does it? Phosphorus creates a energy level close to conduction band edge. This is Ec, this is Ev, and this is the donor level. And the distance between the energy difference between donor level and conduction band edge is such that phosphorus is able to, so phosphorus will have these extra electrons. All of these extra electrons then move to the conduction band of silicon. So, for every phosphorus atom you have one extra electron. So, if you are putting 10^18 phosphorus atoms now, then 10^18 phosphorus atoms will basically contribute 1 electron each. As a result, your N, because of, so number of electrons contributed because of phosphorus will be equal to 10^18 per meter cube. This number is at least 2 orders of magnitude higher, okay. This number is 2 orders of magnitude higher. So, and if you put 1 order of magnitude higher for phosphorus atoms, then again this will increase further. So, basically by putting phosphorus in silicon, you have introduced electron density to higher level. But what it means is that your N increases as Nd increases, but does it mean P remains constant? So, which means your N has increased, but P is similar to this. That does not happen. Because of law of mass conservation, Ni square, which is equal to Np, this is always constant, whether it is for a extrinsic semiconductor or for an intrinsic semiconductor. So, as a result, when you have put in Nd and let us say this Nd is equal to Ne, then we are saying that Ne into Nh is equal to Ni square, or Nh can be, so you can write this P as Nh and this N as Ne, okay. So, for an N type semiconductor which is doped by, let us say, phosphorus, Nh is equal to Ni square divided by Ne, and Ne is equal to Nd, so it becomes Ni square divided by Nd. This is for a N type semiconductor. So, basically you have doping with plus 5 atom, doping silicon with +5 atoms, example phosphorus, leads to creation of extra electrons in Cb, which are basically, you can say, the donated by phosphorus. So, phosphorus is a donor, and as a result silicon becomes N type, especially when Nd is far more than Ni. Okay. Similarly, when you put 3 plus atoms, so now what happens is that when we put 3 plus atoms such as boron. So, now consider a situation like this. You have silicon, okay, these are all covalent bonds. Now, you replace this silicon with boron. So, boron is +3. So, there is basically 1 electron less. So, as a result it takes away 1 electron from silicon. So, what boron does in the energy band gap is, so this is EC, this is EV, this is conduction band, this is valence band. Energetically speaking, boron introduces an energy level somewhere close to valence band, which is called as a acceptor level. So, boron acts as a acceptor because it takes the electron away from silicon. So, electrons from here, they join the acceptor level, as a result creating, so you will create electrons here, and these will be nothing but then holes. So, essentially number of, so if this energy level, if this EA minus EV is small enough at RT, the number of holes created in valence band upon boron doping will be same as donor acceptor concentration. So, this is acceptor concentration in per meter cube. So, we can say safely that P or NH will be equal to Na. So, in this case Ne will be equal to Ni square divided by Na. So, this Ni will remain the same, Ni will remain the same. So, basically in P type you can say Np is NH is much larger than Ne. So, that is why it is called as a P type semiconductor. So, this is P type semiconductor. So, basically in N type you can say doped by phosphorus or 5 plus element, 5 plus 5 element, Ne is much larger than Np, okay, or NH, and sigma as a result will become basically, so sigma is nothing but Ne E mu E plus NH E mu H. So, mu E and mu H are, they could be slightly different from each other, but if Ne is much larger than NH, in that case sigma can be approximated as Ne E mu E, because this is very small. As a result it vanishes. In P type what happens is that it is doped by plus 3 elements. So, basically we are saying silicon in the context of silicon. So, for other semiconductors this would be different. So, NH is much larger than Ne, and here sigma is basically from the same token it will be NH E mu H. Okay. These are the two semiconductors, and if you look at the difference between the donor and acceptor level, so DEC minus ED, which is basically for N type. For P type, we are looking at EA minus EV, and if you look at the difference, the ionization energy, the difference for, so if let us say for phosphorus in silicon, so in silicon we are talking about silicon only, okay. For N type, its phosphorus has 0.044 EV, arsenic has 0.049 EV, and antimony has 0.039 EV. So, these are common dopants that we use, and if you look at P type impurity, for boron it is 0.045 EV, for aluminum it is 0.057 EV, and for gallium it is 0.065 EV, for indium it is 0.16 EV. So, you can see that it is easy to ionize and contribute the holes to silicon using boron, aluminum and gallium, but indium is difficult, but will still work. Whereas for N type silicon we generally use what we call as phosphorus, arsenic and antimony. So, now let us see how does this affect the Fermi level position. So, what happens in semiconductors is that when you dope them for an N type, EC, EV, so this is EF intrinsic, EFI, let us denote it as intrinsic. So, when you dope it and we are saying that this is my ED, okay. So, this is the donor level and this is intrinsic Fermi level. For an N type semiconductor, as you dope it, the Fermi level goes up. So, as a result, the Fermi level for an N type is slightly higher, it is closer to conduction band edge. So, as a result, the Fermi level of N type semiconductor is approximated as, I can write the expression. So, for N type, EFN is equal to EFI plus KT by Q into ln of Nd by Ni. So, as you increase the donor concentration, the Fermi level shifts closer to conduction band as compared to the valence band. So, this is conduction band, this is valence band. For a P type semiconductor, the situation is like this. Again, you can write EC, EV, and here we write EA, acceptor level, and this is the EFI. In this case, the Fermi level goes down. So, Fermi level for P type semiconductor will be somewhere here. So, in this case, you write EFP as EFI minus of KT ln of Na over Ni. So, this KT or KT by Q, you have to see whether you are writing this in EV or some other energy. So, just make sure you take care of units, okay, so that this and that both turn out in EV, otherwise you will have issues, okay. But nevertheless, so this is how the variation of two values will take place. Finally, we look at the temperature dependence of when we look at the conductivity of semiconductors in an extrinsic semiconductor. So, for an intrinsic semiconductor, so let us say sigma as a function of temperature. For an intrinsic semiconductor, basically as you, so we generally plot as 1 over T, so Kelvin inverse. So, for an intrinsic semiconductor, as temperature increases, the conductivity, so you can say this is log of sigma. So, this is for an intrinsic semiconductor. So, essentially we saw that n is proportional to exponential of Ni is proportional to exponential of minus Eg by 2 kT, and sigma is proportional to Ne E mu E plus Nh E mu H, which is proportional to Ne E into mu E plus mu H. So, as we can see, as the so of course mu E and mu H go down a little bit with the temperature, but the stronger effect is seen in Ni. So, the slope of this is basically minus Eg by 2k. So, this is for intrinsic semiconductor. Okay. When you do the same for extrinsic semiconductor, for extrinsic semiconductor, if you plot sigma in, let us say, ohm meter inverse as a function of 1 over T, the plot is slightly different. In the lower region, you follow an intrinsic region, and then it goes through what we, so this is the region which is the higher temperature, it becomes intrinsic. In the, sorry, I said lower temperature, it is higher temperature, and this is exhaustion, and this is extrinsic. So, basically at very low temperature, the material works as a extrinsic semiconductor. In between there is a exhaustion region, which means it is nearly flat, and then at very high temperature it becomes intrinsic. And the reason for that is when you plot n as a function of number of carriers as a function of 1 over T as a function of temperature, what happens is that at very low temperature there are no carriers in any of the band. So, as a result they get excited and they keep increasing until all the donor or acceptor electrons or holes are, so you can say Ne slash Nh. So, this is initial region when, so when temperature is 0, nothing can be excited, as a result electron or hole density is 0. As you keep increasing the temperature, all the donor acceptor electrons get excited, get ionized, they contribute to electrons and holes, and once all of them are saturated, then you reach extrinsic region, and then it remains constant. And once then when you are able to overcome the energy more than the thermal energy or corresponding to the band gap, then you reach the intrinsic region. So, this is what happens, that in between you have a saturation region, because your number of electrons or holes are similar to number of donor acceptor, and until you reach an energy which is corresponding to kT is more than Eg, you will remain in the extrinsic region before you enter into the intrinsic region. So, this is the reason why we see such a behavior in conductivity for semiconductors. So, what we have seen is semiconductors are the materials which have band gap of, so semiconductor materials with band gap, with a band gap less than 3 eV or let us say 2.5. They are different than metals in the sense that in semiconductors the carrier concentration increases with temperature, whereas in metals so as a result conductivity increases with temperature, whereas in metals the conductivity decreases with temperature because of scattering. So, in this course what we have done is we have looked at mechanical properties of materials, talked about elastic properties, then plastic properties, stress strain curve, strengthening mechanism, and finally we looked at basic electrical properties of metals and semiconductors. So, I hope I have been able to provide you basic information about these properties. If you have any questions, you can always get back to the portal and ask TAs or myself questions, and I wish you good luck with this course and hope you have enjoyed doing this course, and you can always write to me if you have any queries. And please do read the books. The lectures are not substitute for any books, these are only so lectures and books go together as it is to improve your knowledge and ability. So, I would recommend you to go through the books which I have recommended in this course, especially George Dieter and Wolf series for mechanical properties, and Material Science by Engineering by Raghavan, or Wolf series again volume by Wolf. So, please go through the books along with the lectures, then only you will be able to fulfill the objectives of the course. Thank you very much.